discuss about squeeze theorem, which is very important in calculus and analysis, and it is used a lot when you want to calculate limits that are difficult to find. The theorem says if some function fx less than equal to gx, gs less than equal to hx, that means if some function g is squeezed between two functions f and h, moreover, you know limit x tends to a, the smaller function fx equal to limit x tends to a, the bigger function hx, which is equal to L, then limit x tends to a, gx will be L. Let's see the picture of this squeeze theorem. This is the function gx that oscillates. However, it is squeezed between two functions f and h. And you know, as x goes to 0, this function f goes to 0, and as x approaches to 0, hx also goes to 0. Then, by squeeze theorem, we can tell limit x goes to 0, the value of gx equal to 0. Are you getting my point? What is the application of squeeze theorem? Okay, let's see one example to elaborate this squeeze theorem clearly. Fx equal to x square cos 1 over x square. Okay, this is the fx function, and this function squeeze between one is x square, other is minus x square. And notice x square and minus x square both approaches to 0 when x goes to 0. And this function cos 1 over x square is continuous function. So by squeeze theorem we can tell easily limit x goes to 0, x square cos 1 over x square equal to 0. Are you getting my point? Okay. Now apply the squeeze theorem mathematically. We all of us know cos 1 over x is cos 1 over x square lies between plus 1 and minus 1. Okay? We cannot evaluate the value of the limit of the function x square cos 1 over x square directly. If we multiply x square both sides, then I will get minus x square less than equal to x square cos 1 over x square less than equal to x square. Okay? Are you getting my point? And we have a inequality which has a value between x square and minus x square. And we know as limit x goes to 0, x square goes to 0, and limit x goes to 0, minus x square goes to 0. Okay? That means both this limit approaches to 0. Therefore, we can conclude this value x square cos 1 over x square as x goes to 0, the value will be 0. That means we can write limit x tends to 0, x square cos 1 over x square will be 0. Okay? Alright. Let's see proof of squeeze theorem. Proof. Let epsilon greater than 0 be given. Since limit x tends to a, fx equal to L, then there exists a delta 1 such that absolute value of x minus a less than delta 1 with x not equal to a, that imply absolute value of fx minus a less than epsilon, that imply fx lies between L plus epsilon, L minus epsilon. Okay? From this line we can write fx greater than L minus epsilon. Okay? Alright. Similarly, since limit x goes to a is x equal to L, then there exists a delta 2 such that absolute value of x minus a less than delta 2 with x not equal to a, absolute value of a is x minus L strictly less than epsilon. Okay? And from this line we can write a is x less than L plus epsilon. Okay? Let delta equal to minimum of delta 1, delta 2. Take delta is so small such that the inequality F, G, H has hold together. Then if absolute value of x minus a less than delta, then absolute value of x minus a less than delta 1 imply fx greater than L minus epsilon, and absolute value of x minus a less than delta 2 imply a is x less than L plus epsilon. Okay? Alright. What can we say about G? Fx less than equal to Gx, Gx less than equal to A is x, and A is x less than L plus epsilon, and Fx greater than L minus epsilon. So we can write this is L plus epsilon, this is L minus epsilon. Okay? That means Gx is squeeze between F and H. Okay? Actually Gx is squeeze between L minus epsilon and L plus epsilon. That imply absolute value of Gx minus L strictly less than epsilon. When we assume epsilon is arbitrary number and we can find a delta which is minimum of delta 1 and delta 2. That means delta is so small such that the inequality F, G, H has hold together. Okay? From this line we can write Gx converts to L. Well, okay. Let's see one most powerful theorem in real analysis, which is very useful in whole of our real analysis. When a greater than 1 and the sequence xn considered a to the power 1 over n, then what will be the limit? Limit must be 1. And notice this value always strictly greater than 1. Then this part will be true. Okay? Since a greater than 1, then we can consider a equal to 1 plus tn to the power n. And notice if a be any positive number, then a to the power n strictly less than b to the power n if and only if a less than b. Okay? And if we choose a equal to 1 and b equal to a to the power 1 over n, and our given sequence is a to the power 1 over n, that means a to the power 1 over n must be greater than 1. Okay? Here I consider a equal to, that means a to the power 1 over n equal to 1 plus tn, and we have to show this limiting value will be 1. That means if we prove tn approaches to 0 as n tends to infinity, then this sequence a to the power 1 over n must be goes to 1. Okay? Now I will use squeeze lemma to prove the sequence tn goes to 0. Look, this squeeze lemma. Since tn greater than equal to 0, what is the upper bound? Look, a equal to 1 plus t to the power tn to the power n. If we apply Bernoulli theorem, then this is greater than equal to tn. That means that imply tn less than equal to a over n. From this line we can write this is less than equal to a over n. Now apply squeeze lemma. This limit n tends to infinity, a over n equal to 0. That means limit n tends to infinity, tn must be equal to 0 by squeeze lemma. Okay? Alright. That means this n, limit n tends to infinity, a to the power 1 over n must be goes to 1. And our proof has done. Okay? Alright. And this sequence a to the power n goes to 0 when a always less than 1. Are you getting my point? Okay. Since 0 strictly less than a, strictly less than 1. Since this is a positive number, then I can multiply both sides by a. Then I will get a square strictly less than a. Since a is positive number, I can also multiply again a, then I will get a cube strictly less than a strictly less than 1. That means this is a decreasing sequence. We all of us know decreasing sequence converts. If xn equal to this sequence xn equal to a to the power n, then since this sequence decreasing sequence, then this sequence will be converts to L. And what is the value of L? Where L equal to GLB of the sequence a to the power n, where n belongs to natural number. Are you getting my point? Okay. And what is the GLB of this sequence? Since a less than 1, a greater than 0 less than 1. That means GLB would be 0. That means this sequence must be converts to 0. Okay? Alright. Now, let's see new theorem. Cauchy's first theorem of limit. This is very useful in all real analysis. Let's see the statement. If limit n tends to infinity a n equal to L, then limit n tends to infinity a1 plus a2 up to an over n equal to L. Have you understood? What is the statement? Okay. Let's see the proof. Let us consider n equal to L plus Bn. Okay. Where Bn tends to 0 as n tends to infinity. That means Bn converges to 0. And limit n tends to infinity an equal to limit n tends to infinity L plus limit n tends to infinity Bn. Okay. Since Bn converges to 0 as n tends to infinity, that means this will be 0. That means is consider limit n tends to infinity an equal to L. Okay. Now we have to prove limit n tends to infinity a1 plus a2 up to an over n equal to L. Consider a1 plus a2 up to an over n. Since I consider an equal to L plus Bn, then a1 will be L plus b1, a2 will be L plus b2, up to an will be L plus bn over n. That is equal to nl over n plus b1 plus b2 up to bn over n. And since bn converges to 0, that means we all of us know every convergence sequence is bounded. That means it is bounded. That means there exists a real number k such that absolute value of bn less than equal to k for all n belongs to natural number. And since bn converges to 0, so for all epsilon greater than 0 there exists m belongs to natural number such that absolute value of bn minus 0 less than epsilon over 2 for all n greater than equal to m. That imply bn less than epsilon over 2 for all n greater than equal to m. Okay, and let's put it 3, let's put it 2. From this line, if this converges to 0, then these terms a1 plus a2 up to an over n must be converges to L. Okay, that means I have to prove this term should be converges to 0. That means I have to prove b1 plus b2 plus up to bn over n minus 0 equal to b1 plus b2 up to bn over n. And we can write this term equal to b1 plus b2 plus up to bm over n plus bm plus 1 plus bm plus 2 up to bn over n. Okay, and we all of us know absolute value of x plus y strictly less than equal to absolute value of x plus absolute value of y. That means this term always less than equal to absolute value of b1 plus b2 up to bm over n plus absolute value of bm plus 1 bm plus 2 up to bn over n. From this line we can write again, if we break the mod then this will be, and if we break the mod then this will be. Okay, and notice here m terms, since is bi bounded, so absolute value of bn less than equal to k for all n belongs to natural number. That means since here m terms, this is less than each bi, since each bi less than k, that, and here present m terms, that means we can write this is mk, and here n, here n, here n, that means this is less than mk over n. Okay, here m terms and here n minus m terms. Notice here m terms and here n minus m terms. And let's see, this is, since bn converges to 0, then absolute value of bn minus 0 less than epsilon over 2. This is true for all n greater than equal to m. Okay, that means for m we cannot apply this. That means this will be true only n minus m terms. We can write this n minus m over n times epsilon over 2. Okay, and here we can apply this condition. Since each bi bounded, since here only m terms, that means we can consider this is less than mk, and since here n, here n, here n, that means we can write over n. Are you getting my point? Okay, let's consider mn over n times k less than epsilon over 2. That means this is less than epsilon over 2, and notice n minus m strictly less than n when m greater than 0. That imply n minus m over n less than 1. That imply n minus over n times epsilon over 2 less than epsilon over 2. That means this is less than epsilon over 2 and this is also less than epsilon over 2. This is equal to epsilon. That means b1 plus b2 up to bn over n should be converges to 0. Are you getting my point? Okay. Now let's see nature of n. Notice, let m1 be positive integer and m1 greater than 2mk over epsilon. How this is possible? Since here mk over n less than epsilon over 2. Since mk over n less than epsilon over 2, if we multiply, then I will get 2mk less than n epsilon, that imply n greater than 2mk over epsilon. Okay? And recall, since bn converges to 0, then there exists a m such that absolute value bn less than epsilon over 2 for all n greater than equal to m. Okay? Also, I will use p equal to maximum of m comma m1. Then the absolute value of b1 plus b2 up to bn over n minus 0 less than epsilon for all n greater than equal to p. Okay? That imply limit n tends to infinity b1 plus b2 up to bn over n equal to 0. And since a1 plus a2 plus an up to n equal to l plus b1 plus b2 up to bn over n. And since this is 0, that imply a1 plus a2 up to an over n equal to l. Okay? And this is our proof. Okay? Alright. Let's see one example of Cauchy's first theorem. Limit n tends to infinity 1 over n 1 plus 2 to the power 1 over 2 plus 3 to the power 1 over, here not n, 1 over 3 plus up to n to the power 1 over n equal to 1, and we have to show it. And here this is very easy if we apply Cauchy's first theorem. Let's see how this theorem will be applied in this math. We all of us know n to the power 1 over n, limit n tends to infinity. What is the limit? 1. Then look, this is the Cauchy's first theorem statement. What is the statement? If limit an equal to L, then limit n tends to infinity a1 plus a2 up to an over n equal to L. Since this is equal to 1, that means limit n tends to infinity one plus 2 to the power half plus 3 to the power 1/3 up to plus n to the power 1 over n over 1 over n equal to 1 by Cauchy's first theorem. Have you understood? Okay. Let's see one example of CSIR NET. Let n be a bounded sequence. then option 1, every subsequence of an is convergent. Is it true? Recall Bolzano-Weierstrass theorem. What is statement of the Bolzano-Weierstrass theorem? I have discussed in my previous video. At first I recommended you please see this video. Bolzano-Weierstrass theorem says every bounded sequence has at least one convergent subsequence. That means option 1 is wrong option, because option 1 says every subsequence of an is convergent. This is wrong. Okay. Option 2, there exists exactly one subsequence of n which is convergent. Is it true? This is also use of Bolzano-Weierstrass theorem. Here tells at least one convergent subsequence. It can be more than one. Let's see one example. xn equal to minus 1 to the power n. This is a bounded sequence, we all of us know. If I consider the event sequence x to n equal to minus 1 to the power 2n, which will be constant sequence 1 1 1, and this converges to 1, and the odd sequence x to n plus 1 equal to minus 1 to the power 2n plus 1, and this is the constant sequence minus 1 which converges to minus 1. This bounded sequence has two convergent sequence. That means option 2 also wrong option, because here has told exactly one subsequence. This is wrong. So option 2 is also wrong option. At first let's see option 4. There is a subsequence n which is convergent. Is it true? This is use of Bolzano-Weierstrass theorem, because Bolzano-Weierstrass theorem says every bounded sequence has at least one convergent subsequence. Okay, that means option 4 also right option. Now see the option 3, and this is very interesting. Option 3 says there are infinitely many subsequence of an which is convergent. Let an be a subsequence which is convergent to L, and we all of us know any subsequence of a convergent sequence will be converge same limit. Okay, since this is a subsequence of n, then any subsequence of this subsequence ank also converges to same limit. Any subsequence of this subsequence ank also converges to L. Okay, are you getting my point? Okay, since this subsequence also subsequence of the main sequence an, so option 3 is right option. There are infinitely many subsequence of n which is convergent. Okay, that means option 3 and option 4 is a right option. Okay, all right.